Again, if you're following my color scheme, we're using pink, dark green, and light green highlighter for today. Those are the things we're going to be using. So like I said last time, once we've learned about circles, we're going to slowly add theorems and postulates for each of the vocabulary words that we learned about. So let's review for a second what a central angle is. Remember that a central angle, we highlighted this pink last time, is an angle whose vertex is at the center and the sides are radii. So when I'm looking at this circle right here, angle AOB is the central angle. The sum of all of the central angles in a circle is 360 degrees. Any circle has 360 degrees all the way around it. But what we learned last class is that we can talk about different, let me add something here. The central angle here is going to be this one. I don't know if you can see that arrow, so we might have to make it a little bit darker. There is an arrow right here pointing to the 59 degrees for angle AOB. So we would talk about the central angle by calling it angle AOB or angle BOA. That's all fine. Now, if you look at the other little arrow here, again, it didn't print very well, so you might not actually see this, but this little arrow is pointing to the pizza crust. Do you remember what it's called when we're pointing at the pizza crust instead of the pizza slice? A minor or a major arc. Very good. So this piece right here is a minor arc. If we were naming that minor arc just to be consistent, we call it minor arc AB and we put the arc symbol above it. But one of the things we know today is that all of the central angles have to add up to 360. So if I wanted to know the larger pizza pie slice, the really, really hungry pizza pie slice, I would just do 360 minus 59, and I'd be able to have this entire other piece of the pizza. Another quick review, let's talk about the types of arcs that we have. So types of arcs, when we were talking about arcs the other day, I used light green to talk about arcs. So if you're following my color scheme, that's light green. There are three types of arcs. You have your minor arc, you have your major arc, and you have your semicircle. A minor arc is an arc that measures less than 180 degrees. A minor arc is the same measurement as its central angle. So the central angle and the minor arc measure the same, and it's named by 2 points. A major arc is an arc that measures more than 180 degrees because it's a bigger arc. And semicircle is specifically one that measures exactly 180 degrees, and it is named by 3 points. So if we look at this image right here and we named some of those points, the first one right here that's next to AB, is that a major or a minor arc? Minor. So we're going to call that minor arc. And since we're naming it, it needs 2 letters and the arc symbol above it. But if we wanted to name a major arc, specifically the major arc that goes all the way around the circle this way, how would I name that major arc? Where does this major arc start? A. What point does it go through? E or D, true. And where does it end? At B. So either you could name it a EB or backwards BEA, or a DB or DBA. As long as the letter in the middle is actually in between it, that does tell me the correct direction to travel around that circle, so it's telling me the major arc. What if we talked about a semicircle? 180 degrees. So if we wanted specifically the name of the semicircle here, we would say, and I'm going to look at this one here in the bottom. If I wanted this semicircle, where does it start? E. Where does it go through? And where does it end? B. So the semicircle would be named EDB with a little arc above it. That is the semicircle in this picture. So knowing that these central angles all add up to 360 degrees, and that the central angles and the arcs are the same measurement for the same pizza pie slice and pizza crust, we have what's called the arc addition postulate, and it says that the measure of an arc formed by 2 adjacent arcs is the sum of the measure of the 2 arcs. And that's a really fancy way of saying you add the angle measurements together. So if I'm trying to find the measure of arc ABC, I'm looking for this measurement right here, this major arc. So what I can do is I can take the measure of AB and I can add the measure of BC, doing those two things separately, and it will give me the measure of everything. And that makes sense because it looks like it's two pieces added together, and in fact it is two pieces added together. So you add both arcs together and voila, you have the larger arc. So let's take all of this information and let's look at some practice problems. I've done this first one for you so you can see. It says find the measure of each arc of circle P where segment RT is a diameter. I need you to make sure you recognize that if it tells you that RT is a diameter was our blue word. I know I didn't warn you about blue color, but blue is our diameter. That means we know that this is part of, it's creating my semicircle. So that means that this side is 180 degrees and this side is 180 degrees. So if I specifically ask you for TS, I just want this arc right here. We know from the arc addition postulate that these two arcs added together will make 180 degrees. So what I did to find the missing piece is I said, well, let's do 180. That's the whole thing. And subtracting off the 110 that I know, and I get 70. So we can add that 70 to our image. It's always good to add numbers to your image as you find them. So arc TS is 70 degrees. The central angle TPS is also 70 degrees. Those are always going to be the same angle. If I look for RTS, starting at R, going through T, ending at S, I know I cross this semicircle, which is 180 degrees. Why don't we add that to our picture? This is 180 degrees. And I'm also crossing through TS, which is 70. So the arc addition postulate tells me I can add these together. Voila, I get 250 degrees. And the last one, this RST, if I look, RST is a semicircle, so I should automatically know that's 180 degrees. But using the arc addition postulate, it's RS plus ST, so that's 110 plus 70, which is 180. Awesome. Okay, so using the arc addition postulate, I want you to try number 2. We're going to pause here for a second. We're going to find the measure of each arc. Then tell me if that arc is a major, minor, or a semicircle. I actually want you to try these, so go ahead and pause and try here. For number 2, part A, it wants me to find GE, which means I'm finding the measure of this arc here. Well, since the central angle here is 26 and the central angle here is 78, the arc that combines those together I can find just by doing 26 degrees plus 78 degrees. When you do that, you should get 104 degrees, which is the measure of angle of arc GE. Now question, does that make it a major, minor, or a semicircle? Minor, because why? Less than 180. Fabulous. For HF, I know it's really tempting to look at HF and try to call it a semicircle because it kind of looks like it, but they did not tell us in this question that HF is my diameter. So we actually have to do the math numbers. Remember, we're not trusting our eyes in geometry, we're trusting the numbers. If I look from HF, that includes the 78 degree central angle and the 95 degree central angle. But if I add those together, do I get 180? No, I get 173. Which again, is that a major or a minor arc? Minor because it's less than 180. It looks like a semicircle to the untrained eye, but it is not. Semicircles are exactly 180. For arc EFG, I look from E to F to G. And we're going to have an issue here because I know from E to F that central angle is 95 degrees, so the arc is 95 degrees. But do I have anything listed for G to F? No, so we need to figure it out. So my question for you is, what should a whole circle add up to? 360. So we can use that fact to find the missing side. So we know that the 26 degrees plus the 78 degrees plus the 95 degrees plus my missing degrees should be equal to 360. Now this is technically a solve for x, But it's so simple, we're not even going to use the box method. We're just going to subtract all these values away from 360, which means I'm in a calculator going to do 360 minus 26 minus 78 minus 95. That is what you would do if you did a box method question here, but it's way more simple than that. And what do you get when you subtract all these values? Yeah, just the subtract the values, don't get ahead of me. 161. So if I go back and add that to my image, because it's always good to add things to your image, the central angle RFG and the arc F to G are 161 degrees. So if I actually answer the question here, it says that if we go from E to F, how much should that be? 95. And then from F to G to finish it out? So we're going to add those two numbers together. And I wrote kind of big here, so I'm going to back up so I don't run out of space for myself. And I'm going to put this equals 161 here. We know that 161 plus 95 is the number that Joseph said already, 256. So this is a 256 degree angle. Is that a major, minor, or a semicircle? Major. Why is it a major? More than 180. Fabulous. Now, number 3, I started to set up for you because it takes the same idea from number 2, part C, but adds an actual algebra question to it. It says to find the value of x and then the measure of arc AB. So just to keep in mind, we're going to find x, but we're also going to need to make sure we locate or find the value of arc AB, that minor arc. So I've started to set this up, but I didn't finish. If you notice, I took 5x, which is AB. I took 40, I took 70, and I took 75 plus 2x. And I just added them all together. What should they be equal to? 360, because around a circle is always 360 degrees. So you need to help me out and finish writing that in. So 360 degrees. This is an inverse operations or box method question. There's no more parentheses for us to have to distribute, and I just need to solve for x. We'll do that together. How many terms up here have an x attached to them? How many terms up here do not have an x attached to them? More than 3. 4. So I need 4 boxes over here so I have a spot for everything. I start dragging and dropping. This is 5x. The 40 goes all the way over here, negative 40. 70 also, boop, all the way over there, negative 70. 75, cross the line, change the sign. 2x, no cross the line, don't change the sign. And 360, no cross the line, do not change the sign. We're pros at this point, so we add the numbers on the top, that's 7x. We add the numbers on the top, that's 175. I divide by what? 7 to get that x is equal to, and I'll fast forward for you because I know you know how to use a calculator, x is equal to 25. Woohoo! We got part of this question because it did ask me to find x. But what else did this question ask for? And this is where a lot of us get stuck. When there's a step beyond just solving for x, what do we do with the x value? Plug it in. It usually involves multiplying. So if I'm finding the measure of AB, I'm going to take 5x, because that's the measure of AB. Sorry, AB is equal to 5x. But instead of x, what am I going to put there? 25. And so in my head or in a calculator, I'm going to do 5 times 25. And I'm going to get that the measurement of arc AB is 125 degrees. So for a lot of these questions, it's not just going to stop at solving for x. It is going to probably ask you to plug it back in and find the value of some arc or chord as we turn the page over.
Do we always do this with these type of problems? So we take everything, add it up, and then multiply to the...
Yes, so if it's asking you for all of the arcs or having to do with all of the arcs, every circle adds up to 360 degrees. So you can add up all of the pieces that you know or don't know, because the x we don't know, and set them equal to 360 and solve. Because circles always add up to 360. Yes? Let's flip to the back and keep going. On the back, we have a whole bunch of theorems that have to start doing with chords and arcs. And they sound really complicated, but if you think about it really simply, they're actually really pretty simple. Your first one is called the congruent circles rule. It basically says that circles are congruent if and only if they have equal radius, which makes sense to us. If they are a different size, meaning they have a different radius, they are not the same kind of circle. Duh, one's going to be bigger than the other. Then we have a congruent arcs rule. And a congruent arcs rule is going to say that arcs are congruent if and only if they have equal measures, like numbers, they're the same number, and they're on the same circle or congruent circles. So we ask ourselves two questions in numbers 4 and 5. It asks me to determine whether the indicated arc measures are congruent and to justify. The first thing we ask ourselves is, are these arcs that we care about the same measure? So let's highlight arc CD and arc EF. Are those arcs the same measure? Yes. I need two yeses. I need a yes for this first question. I need a yes for the second question for us to say that they're congruent. Are these arcs a part of the same circle? Yeah, they're like literally on the same circle, right? Don't overthink it. This is a yes, yes, which means we can write the statement that yes, arc CD, sorry, I wrote the wrong letter, arc CD is congruent to arc EF. That's what we were trying to prove. Now you have to have a yes for both the same measure and the same circle. If you have a yes, no, mm-mm. If it's a no, no, mm-mm. If it's no, yes, mm-mm. So if we look at number 5 looks weird. Your spidey senses should already be going off. But if I'm checking to see if arc RS and arc TU are congruent, we have to ask ourselves two questions. Are they the same measure? What's the angle creating that arc RS? 90. What's the angle creating arc TU? 90. So do they have the same measure? Yes. And just because that's different, let's put a little note to ourselves that says they're both 90 degrees. But then we ask ourselves the second part of this. Are they a part of the same circle? No, look how I highlighted it. RS is a part of this small circle and TU is a part of the big circle. So they're not a part of the same circle. And are the circles they're a part of the same size? No, like this one's obviously smaller than this one, yeah? So their radius will be different lengths, so we're going to have to say no to that. Which means that overall, those two arcs are not congruent. We would say no, arc RS is not congruent to arc TU. Our next theorem starts working with more than just arcs and starts working with chords and arcs. So highlighting wise, if we look at the color scheme I used last time, chords I used dark green for, and arcs I used light green for, which yes is kind of annoying because they're the same color, but they're technically different. One is dark, one is light. But the congruent chords and arcs theorem says if two minor arcs, my arcs, are congruent if and only if the chords are congruent. The chords that make them are congruent, and vice versa. So you see those markings here on this circle. One of them, the chords have 1 tick mark, and the arcs have 2 tick marks, showing that they're congruent to each other. And it's a really pretty simple rule to use. In number 6 and 7, we're using the same circle here. Let's go ahead and highlight that circle. We have chord AB, and we have chord BC. What do you notice about those chords? They're the same measure, so we're going to put 1 tick mark on those chords because we know that they're the same measure. They're both 9. If they are the same measure, we then learn that the arc connecting them, oh, I meant to highlight, not right, highlighting, AB and CB, those are also the same. Not the same as AB and BC, but the same to each other. One's curved, one's straight. They'll never be the exact same, but they're same to each other. So now that we've noticed this at our image, we can answer the questions. Number 6 says if the measure of AC is 150 degrees. So let's look. AC, let's add that to our image. That's right here, 150 degrees. It wants me to find the measure of AB. Okay, question for you. An entire circle, how many degrees is it? 360. If I want to take away this piece, so I'm only looking at the pieces that I've highlighted, I'm going to do 360 minus 150, which means that I have 210 degrees for both of those arcs to exist. But we know those arcs are the same. So what can I do with the 210 degrees to figure out what one of them is if they're both the same? Divide by 2. They have to be the exact same, so I can take 210 and I can divide it by 2, which is 105 degrees. And I know immediately that the measurement of AB is 105 degrees. They have to be the same. So this one is 105 degrees, and this one is 105 degrees. For number 7, it's actually a different question, but it's using the same picture. So it might be confusing for us to have had these numbers listed on there. So just because we're doing a new problem and I have an ability to erase, I'm going to erase these numbers we just put down. I know you're like, Miss Quigley, we literally just wrote those down. I know. We're using the same picture but with different numbers. This time in number 7, it says if the measure of AB is 110 degrees. So arc AB is 110 degrees. It wants to know the measure of BC. Don't think too hard about it. What is the measure of BC? Ooh, that's BC, the chord. I want the arc BC. Notice, watch again on the screen. If this arc is 110 degrees, what's this arc? 110. They have to be the same, so they're congruent. I don't even have to do any work. I know that it's 110 degrees. Our next theorem. We got a few more theorems left today. There's so many theorems when it comes to chords and arcs. The perpendicular chord bisector theorem. Ooh, that's a lot of words. If you look at the image though, it says that if a diameter is perpendicular to a chord, perpendicular means meets at a 90-degree angle, bless you, then it bisects the chord and its arc. What does the word bisect mean? Yeah, cuts it into 2 equal pieces, or cuts in half. So what that means for us is if that you see a 90-degree symbol on a chord that crosses a diameter, then that chord is perfectly cut in half by the diameter. So in practice, what that means, like number 8, it says find HN, then find X. So I see that I have a chord, and I have a diameter, which is technically also a chord. Those chords are perpendicular to each other, which means immediately that I can put the tick marks on the chord that is not the diameter, and I know that it is bisected. So this question wants me to find HN. HN is this little bit right here, which is perfectly congruent to this little bit right here. That's what the sentence says. HN is congruent to NK. So how much is HN? 7, because they're the same. Then it wants me to find X. But X is situated on these arcs. But we know that arcs created with the same angle on the same circle are congruent. So I can put 2 tick marks on these arcs, which tells me that they are congruent, which is what this statement says. And then I can just set 11x equal to 70 minus x and solve for x. Now I skipped a step here because I ran out of room, but this is a box method or inverse operations that I know you know how to do. While I answer this call, you're going to have number 9 to try. I want you to find x and find the length of PR. For this question, to find x, we should notice that there is a chord here, chord PR, and the diameter SQ, which again is a chord, but it's specifically the diameter, and those meet at a right angle, which means that this chord and this chord are congruent. If they're congruent, then what we can do is we can take their measurements and we can set them equal to each other. 2x minus 4.1 equal to x minus 0.5. We're not going to panic because there's decimals because we have the box method. There are two terms that have x's in them and two terms that do not have x's in them. So I give spaces for both. This is going to be the 2x spot. Cross the line, change the sign. This will be negative x. No cross the line, no change the sign. When we combine these, 2 minus 1 is just 1x. And 4.1 minus 0.5 is positive 3.6. You can divide by 1, but it doesn't change anything, so we know that x is equal to 3.6. If you solved this question, did you get it? Yes. Yay! Love to hear it. Now that's part of it, but remember this had a part 2. It said to also find the length of PR. PR is that chord. What are we going to do with x now that we've found it? Plug it in. So what I'm going to do is I'm actually going to only plug it in to the value of OR. And you'll see why in a second. If I plug it into OR, OR is equal to x minus 0.5, which I can replace with the x, 3.6 minus 0.5. And I get that that measurement is 3.1. Now I only did this for part of it because they're congruent. So if this part is 3.1, how much is this one? So what's the total of PR? It's going to be 3.1 plus 3.1 because it's both pieces, bless you by the way, which is going to be 6.2. That should be the value of PR. So again, all I did once I found x is I plugged it in here. You could plug it into both and add them together, but to go faster for me, I plugged it in here. Got that this one was 3.1. And if this is 3.1, then this is 3.1, so I can add them together to get the entire length PR. Our last theorem here is called the equidistant chords theorem. The equidistant chords theorem says that if two chords are congruent, if and only if they are equidistant to the center. So we have these two chords. These two chords are going to be the same length if, and I'm going to zoom in to highlight here, if this little piece and this little piece are congruent. So we can put the little congruent things here, which force us to have congruent markings on my chords. I know that's really small. This problem is a little bit difficult, so I've given you some steps to follow so that when you're looking back at your notes, you'll be able to see what we did. Number 1 says, since UV, which is here, and WX, which is here, since they are both equal to 20, you see how they're both pointed out to be 20, we know that they are congruent, which forces me to know that these little perpendicular bisectors are also congruent. So I can put the tick marks on those. Which means that I can put 4x minus 5 equal to x plus 4. Now I've shown box method a few times, so I'm going to do inverse operations on this one, but again, you can always choose to do box method. In inverse operations, we're going to subtract x to get it to the other side, which means I end up with 3x, drop down minus 5, drop down 4. I add 5 to both sides to get the x terms by itself, which means this is going to be 3x equal to 9. And just like the last step of the box method, the last step here is to divide by 3. So I get that x is equal to 3. Again, if you don't like inverse operations, once you get it set up, since they're congruent, that means they're equal, you just box method. Once we have x, we need to know this distance here. So we're going to plug in x to find the line YO, which means we're going to take 4x minus 5, and we're going to replace the x with what? 3. So 4 times 3 is 12. 12 minus 5 is 7. Now, I might have gotten away from this, so let's rewind a second and realize what it's asking for. This question is asking for the radius. None of these measures that are listed on this triangle are the radius. The radius should go from the center to the outside point. So I've drawn in a radius now. Do you see how this makes a cute little triangle? In fact, I'm going to highlight this cute little triangle yellow. I know, again, I didn't tell you to get a yellow color, but I think it would be helpful for us to see this as a cute little triangle yellow. So what we're going to do in step 3 is we're going to take that cute little triangle and we're going to make it look like an actual triangle on our paper. So if I look at this, this is my cute little triangle. Make sure you can see it all. Here. We don't know the radius. We just found out one of the other sides. What did we find out was one of the sides of this? What is this measurement right here? We just found it. 7. So on my side, I'm going to put a 7. I also need to know now this little bit right here. Okay, my question for you. If this whole thing is 20, how much is this bit? 10. So now I have my entire triangle figured out. I have a side worth 7, and that's a weird looking 7. Let me try writing it again so it doesn't look like a, I don't know what. We have a triangle with sides that are 7, 10, and a radius that we need to find. That's a right triangle, so all of our right triangle geometry, which we learned previously, matters. So we're going to use Pythagorean theorem to solve for that missing r. Pythagorean theorem, to find r, we're going to do the square root of those sides squared. And at this point, it's when you turn to a calculator. So in our calculator, you're going to put square root. You're going to put parentheses 10 squared plus parentheses 7 squared. Yes, the parentheses are important. You will get a decimal for most questions like this because we're taking square roots. They're usually kind of cute. This one, I believe we have to round. What did we get for this one? 12.2, I'll add one more decimal, 12.21. So all in all, my radius is 12.21. There was 4 steps to do this question, which does make it challenging, but I think we have the ability to do it. So again, just as a review of this question, because we're looking for the radius, we know that that had to be drawn onto the image. Our chords are congruent, which means these distances are equidistant. That's the theorem. Since they're equidistant, I can set their expressions equal to each other and solve for x. Once I get x, I can use it to find the distance YO by plugging it in, which then creates a cute little triangle with a height of 7, a flat line of 10, and a radius that's missing. That's over here. Then we use Pythagorean theorem to solve for that radius, just by sticking those side lengths of the triangle into the Pythagorean theorem itself.